Then I will welcome our next participant, Abdulla Mohammed from the USA.
Hello, everyone. My name is Mohammed Abdulla. I'm from the United States, and my research was on a fine classification of second minimal odd orbits. Now, the main inspiration for this problem comes from the fact that scientists, one of the main problems in science is modeling the behavior of natural phenomena over long periods of time. This is a problem in many fields, from predicting the weather to predicting the turbulence of a fluid, to predicting how the population of an animal species changes in an ecosystem over a long period of time. And one of the main problems is that a lot of these systems are inherently chaotic, which means that even though they adhere to a very simple set of rules, the adherence to these rules is so strict that even the tiniest change in the measurement of an initial set of parameters can cause a drastic change in the long-term behavior of these functions. So let's take a look at one very specific example. This equation shown here is frequently used to predict the population of an animal species in an ecosystem over some long period of time. The population at any point in time, n plus 1, is given by 4 times some fixed parameter lambda, which is meant to characterize the ecosystem, times the population at the previous point in time, n, times 1 minus the population at point in time, n, which describes the difference between the population and the carrying capacity. So what happens when we look at the long-term behavior of this function? Well, we see that for low values of lambda, if we look at the asymptotic behavior, if we iterate this function an infinite number of times, we're going to approach something called a fixed point. This means in physical terms that the population is going to reach a value and then remain stable at this value no matter how many times we iterate this function. At lambda equals 0.75, this process undergoes something known as a period doubling bifurcation. So now, rather than approaching a singular fixed point, it's going to fluctuate back and forth between 2 points. Now, in physical terms, what this means is that the population has 2 possible values it can take that swings back and forth between. Now, as lambda approaches 1, the system becomes more chaotic. And if you remember the definition of chaotic behavior, that means that as lambda changes just a little bit, the long-term behavior starts to change more and more. So we see that these period doubling bifurcations start occurring closer and closer together, and then as lambda approaches 1, we see suddenly it becomes extremely difficult to predict what the long-term behavior of this system will be. However, we know that there is still some mathematical order in the system. For instance, we see the presence of a 3 orbit here, which means that at some point in this whole chaotic mess, the population will swing back and forth between 3 population values for some reason. So what I'm investigating is whether or not there is some mathematical order to the system. Specifically, is there some mathematical law of distribution that can describe the appearance of periodic windows within the chaotic regime of these iterative functions used to describe natural phenomena? So let's say that we fix lambda at a certain value. We have 0.94 something, and we start with an initial population value of half the carrying capacity, 0.5, and then we iterate this function. And we find that after 7 iterations, we go from 0.5 to 0.944, etc., through this process back to the initial point, 0.5. This means that we have a periodic orbit of period 7, and we're going to try to model this periodic orbit in a completely different kind of structure. Rather than viewing this as an algebraic system where we simply iterate this function, we're going to take each of these points and call them fixed points. We're going to label them in numerical order from beta 1 to beta 7 and place them on the real number line. And now we're going to describe some continuous process that connects these points along this real number line, and this is known as a continuous endomorphism, which is a different field of mathematics. So we see that beta 1 is going to map to beta 4 because 0.5 matches to, we see here. So this structure that describes how these fixed points along some real line connect to each other in one period, in one cycle, is called a continuous endomorphism, and it's just a different way of describing the same idea. Now, the structures of these continuous endomorphisms are more well understood. There are different mathematical theorems that describe different properties of the system. For instance, Tchaikovsky's theorem describes introduces the concept of minimality in the system and describes how the appearances of different periods in the system relate relate to the appearances of other periods. And my research was focused on a very specific kind of structure called a second minimal structure. And I was essentially able to show that for any second minimal orbit of length 2k plus 1 of odd length, there are 4k minus 3 possible kinds of structures it can take. And the main significance of this result is that it allows us to derive some connection between these two different fields, between the fields of cyclic orbits of continuous endomorphisms and within cyclic orbits in chaotic iterative functions. And it offers us a deeper insight into the nature of how chaotic functions behave. Thank you.
Thank you very much for this speech. Do we have any questions? Over there, yeah.
How does knowing the behavior of natural phenomenon help humanity?
Well, the main problem with chaotic systems is that basically any kind of natural phenomena that does behave chaotically is extremely difficult to predict over long periods of time, because when we make these predictions, we have to base them off of initial measurements. And because these initial measurements always have some degree of inaccuracy or imperfection at the beginning, and the long-term behavior of chaotic functions changes drastically with these tiny imperfections, it's very, very difficult to predict what the long-term behavior of these functions is. So one key to having more accurate predictions is just understanding better the nature of these chaotic functions, of these iterative functions, and understanding more about the mathematical order of these chaotic systems. And yeah, the main idea is that we have to understand more deeply, more in depth, what the actual nature of these systems are. And the main result of this research is that it offers a new way to look at these functions and a new way to understand the order within these functions.
Thank you.
Okay. Okay, then I assume there's no more question. So thank you very much.